Good afternoon, everyone. My name is Sharon White, and I'm with BLT. I want to thank you all for joining us today. Today's 30-minute webinar includes discussing interfacing DDR with programmable logic, a live demo, and then a Q&A session at the end. Please note that this webinar is being recorded. We ask that everyone use the chat panel on the side of your Zoom window for questions, and we'll get to them at the end after the demo. Before we get started, I'd like to briefly tell you about BLT. BLT has been in the FPGA business for over 30 years. We're an engineering company providing custom electronic solutions for commercial and government IC and aero applications. We design custom chips, embedded software, circuit boards, and complete systems. BLT also trains 1,000 student days a year and works on dozens of board, FPGA, MPSoC, and ACAP projects each year as well. Some of our more notable projects include work on the Mars rover, designing the prototype for HDTV, helping develop satellite radio, and implementing one of the earliest RF SoC designs ever done. Our designs are in space, undersea, and everywhere in between. We're a Xilinx authorized training provider and a Xilinx certified alliance member. Today's presenter is Ellie Rosen. Ellie is one of our engineering managers at BLT, primarily focusing on ACAP, RF SoC, and MPSoC designs for both commercial and defense applications. In his prior roles, Ellie is specialized in custom ASICs, ARM-based processor applications, and ACAP-based machine learning applications. Like many of you here today, he has led and worked on dozens of complex systems, many of which utilize high bandwidth DDR interfaces for both ACAPs and MPSoCs. Thank you, Ellie, for taking your time today to show us how to incorporate these techniques into our ACAP designs.
Thank you, Sharon, for that introduction, and welcome everyone to today's webinar. Happy to see you all here today. So we're going to cover a few things. I want to get us all up to speed on some of the architecture around the NoC, or network on chip, and how Xilinx brings the network on chip in a dedicated fabric so that you can just pipeline your designs and move large amounts of data everywhere between these Versal devices as efficiently as possible. Then I'll show you guys in Vivado a demonstration on how to configure the DDR interface through the NoC to the SIPs, the control interfaces and processing system block for the Versal device, as well as an example of how to connect a peripheral and the programmable logic to talk directly to a DDR interface as well. At the end, we'll have some time for a question and answer session, and if there are any questions that come up throughout this, please feel free to paste them in the chat and we will get to them at the end. So with that, I'd like to give a little overview of how the network on a chip works. What the network on a chip is it's a dedicated fabric that is hard silicon inside of these Versal devices that are interleaved between the scalar engines, the adaptable engines, and the intelligent engines in the Versal architecture. Now, because this webinar is only a half hour long, I'm going to make some broad assumptions that you may already have some familiarity with the Versal architecture. If there are any questions relating to that at the end, we can always talk about that after this course. We do offer training for that as well. So given the NoC framework, we're able to move data quickly between all of the engines on the device. We're also able to talk directly from the NoC to DDR memory controllers. That's what DDR MC stands for. And the DDR memory controller handles all the bottleneck management of any of the peripherals that may want to talk to the DDR interface. Finally, because it is dedicated silicon resources, it's guaranteed to meet timing. Xilinx has already done the floor planning for the network on a chip, and it meets timing for up to a little over 1 gigahertz. It doesn't require any additional PL routing resources in order to be able to interface with this NoC architecture. So here we can see a more expanded view of what the NoC looks like on the inside. And I'm going to go through the various components here and how they all play along with each other. The NoC is a series of horizontal and vertical NoC spines. These are the spines where your packets of data, the packets of data over a NoC interface are known as flits. And these flits are packetized versions of either AXI memory mapped or AXI stream transactions. For any of you who have possibly worked with other Zinc type architectures like the MPSoC or the Zinc 7000 series, you may have worked with an IP known as the AXI interconnect. The NoC has some similarities to the AXI interconnect, except in the Versal architecture, this is all dedicated silicon. So here for this dedicated silicon, this silicon operates at a little over a gigahertz, like I said, and it has a high-speed hardened path for packetizing your data and bringing it between the various units and peripherals inside of your FPGA design. So some terminology that's important when we're talking about the NoC. I already mentioned the HNoC and the VNoC, which are the horizontal and vertical NoC spines. Those comprise of the network on chip architecture. We also have NoC master units. And so these are your entry points into the NoC superfast highway, if we want to call it. This will organize your data, bring it through all the switching networks, and allow it to get to the destinations that they're expected to go to. Then we have the NoC slave unit. And so this is your off-ramp from the information highway here. So this will depacketize your data back into either AXI memory mapped or AXI stream formats. The little squares that we see between intermixed all of the horizontal NoCs and vertical NoCs are your packet switches. So here there is logic here to basically handle the routing between all the master units and all the switching units across any of the possible physical silicon die that exists inside of this silicon package. Not shown on this image is the NoC inter-die bridge. And so this is how we can do NoC to NoC communication between physical silicon devices. And what Xilinx does for you is they take care of all of this. So you don't even have to think about it, even though we might be doing something that, in paper might actually sound really complicated to do. The tools already handle this for us. And then finally, as part of the NoC, we have the DDR memory controllers. And so if anyone here is familiar with the MPSoC type architecture, there used to be, you would have a memory controller associated for the processing system. You could also instantiate your own memory controllers in the programmable logic, and you'd have to use an AXI interconnect to interface them. For a Versal device, you would have this you'd have this DDR attached to the NoC. That way, either the processing system, any of your peripherals can all share the same DDR. And you're not just limited to one instance of DDR. You can have multiple DDR instances connected to a single NoC. And I will show you that in the demo. So to the meat of what we're trying to do today, as a designer, how can you interface with this NoC? And you do that by using the IP Integrator tool in Vivado. Now, one of the interesting things about the NoC is that it is logical IPs that represent different chunks of physical silicon. And so normally where you might have one IP that represents, let's say, a single 10 gig Ethernet subsystem on a transceiver, here we can have multiple NoC instances where when the validation runs and the NoC compiler runs, it'll compress it all down into a single NoC solution representing everything that you tried to design in the IP integrator. So you can have as many NoC instances as you'd like, any kind of configuration you could think of, and then the NoC compiler will handle bringing that all down to a single solution. So just to give a little example here, imagine I have a design that has a lot of peripherals that all want to talk to each other. And we could see here that the total resources used are 70,000 lookup tables and 70,000 flip-flops. Of that, roughly half are for interconnect resources. So imagine if you have an AXI interconnect, about half of the resources here are consumed just to handle that interconnect. But now with these Versal devices, and if we enable the NoC, we can see that we now use 0 resources for the interconnect because the resources are all just the physical instantiations of the NoC. And so we go from 50% overhead for the interconnect to now no longer requiring that overhead. Also here we can see that the representation of that interconnect is now marked by these little boxes here. These boxes are your NoC switches for moving data between the various NoC endpoints, the master units and the slave units. So how you use the NoC would be to instantiate the NoC IP. It would just go into IP search, you type AXI NoC, and then that will load in an instance, and you can configure it to either be memory mapped or AXI streaming. You can also run block automation, and I'll be showing an example of that to very quickly get a design up and running utilizing DDR without having to go through a lot of complex menus or spending a lot of design time. Before moving on to the demo, I just want to give a generic example for how data moves through the NoC. So you might have a master or initiator device. Those types of devices can either be a processing system core, it could be a DMA, an input device, some IP that you might have in the programmable logic. For this demo, I'm going to use the AXI traffic generator as a mechanism to, in the PL, generate hardware that'll go into the device. Or it could be a AI engine, part of the Versal series, talking over the NoC as well. These devices can communicate over AXI 3, AXI 4, AXI streaming, and so forth. They then enter the NoC in through a NoC master unit, and that will packetize the data. For example, if I have an AXI stream interface, it's going to break it down into packets, or what they call flits. And then these flits will go travel through a VNoC or an HNoC to the physical routing and the switching network. And then it will go to a NoC slave unit to depacketize that data, either keeping it as memory mapped or into the slave format if that's where it was coming in as. And then your slave peripheral will consume that data. Most importantly is that the NoC handles all the clock domain crossings. So as you'll see in the demo, there are a lot of clocks involved for how data gets onto the NoC and how data gets off the NoC. The key here is that inside of the NoC, data is moving with that 1 gigahertz or so clock to get data where it needs to go as quickly as possible. But then it will handle the clock domain crossing to bring that data into the relevant clock domain that you're using in your application. So to the user, you see either an AXI full memory mapped or an AXI streaming interface. And if you've used IP Integrator before, just dragging and dropping, creating the lines to connect your IP, the same validation rules apply, and you can treat it as a regular AXI interface. So hopefully that gave a good overview of what the NoC is at a big picture and how we're going to move data around between the various slave units and master units. So with that, I'll go into my live demo. So I've sped up a few things on my side just to save us a little bit of time. I've created 2 examples here. The first one's going to be an automated flow, and the second one is going to be from scratch. Opening up the automated block design, all I've done is I've placed in an AXI NoC, and I'm doing this just to speed us up a little bit. And what I want to show here is how you can very quickly interface with DDR just by using the Run Block Automation tooltip. By running this, it'll open up a wizard. And then in this wizard, I'm going to tell it that I want to use a SIPS interface. So I want to talk to the control interface and processing system block. I'm also going to turn on a ACAP traffic generator as a means to show an example of programmable logic being used. We're going to use DDR, and then I can just hit OK. So this will take a few moments, but what it's going to do is it's going to plop in all of the various IPs that I just selected in the wizard, and then it's going to connect the wires for them as well. All right, so if I just clean this up a little bit using the tools up here, I can see that I now have a SIPS block with the 4 cache coherent interconnect ports connected to the NoC. I can also see that it's utilizing the DDR interface and an ACAP traffic generator. And then I am just going to clean this up completely by telling it to use the clock 100 megahertz that I've specified here. I'm basically taking some large assumptions so that it will clean it up as much as it can. And we're just going to have that automatically select every. So now if I validate this block design, there should be no errors. And this is the result of the NoC compiler that we're seeing behind the scenes here. So it's almost done. It just has a little bit more to do. And while that's completely validating, okay, we don't have any warnings. What I could show here is that we now have the SIPs. These blue boxes are our NoC master units. And so here, this could be the low power domain one. Then we might have the cache coherent interface here. And down here, the green box is the DDR memory controller. And then over here, we have a master unit representing something connected in the programmable logic that has interconnect resources that make its way all the way back to the memory controller. So there are, of this entire NoC, there are quite a lot of places here that are not currently being used, and that's because this is a very small example. So you can see all of these NoC interfaces over here are for things connected to the programmable logic. Then down on the bottom here, we have 3 additional memory controllers that aren't currently being used. So I believe there was a question here about the number of memory controllers that we can support, and there are up to 4 memory controllers on this part. And then we have up top here are all of the AI engines, because I'm using one of the AI Edge parts on the VCK 190 evaluation board. So I just wanted to use this as a quick demo to say, oh, look, you could have your design, and just by running a single block automation, I'm already connected to DDR. But the reality is, not all of us are this lucky, right? Oftentimes, we're going to have to create our own block designs, create our sources from scratch. So I want to show you how to do that. So let's see how to do the NoC from scratch. So I've preloaded a few IPs here just to save us a little bit of time. I have a ACAP block RAM controller connected to an embedded memory generator that's about 8K of memory. I have 2 ACAP NoCs because I want to show you an example of how if you have 2 NoCs, they can still use the same dedicated hardware, and the compiler, condenses them all down into one physical unit. I have the ACAP traffic generator to show connection to the DDR like before. I have a synchronous reset, and I have my SIPS block. So I'm going to go into the SIPS, and I want to turn on a few ports that we're going to use to connect to the DDR. Now, I've already preset this SIPs to use the fixed and dedicated hardware that comes with the VCK 190, and that's to save us a little bit of time. I'm going to look at the PS and platform management controller settings. And then here I'm going to specifically target the NoC. And in this case, I want to turn on the coherent interfaces for the PS to NoC. That's going to give us 4 cache coherent ports. Oftentimes, you're going to want to use a cache coherent port if you're running software on either the A72s or the R5 processors to talk to the DDR. Remember, your software will have to run through that DDR as well. And then I'm also going to turn on this RPU to NoC interface so that I could have the processor talk to that block RAM. All right, so I'm going to click Finish, and then I will click Finish again. All right, so now we had a lot more ports created, and you can notice that for each of these ports, there's a complementary AXI clock provided for the domain of that interface. So let's look at the PSPL NoC with DDR. Because I'm using a VCK 190, this is a board-aware design. So I can go under the board interface here and select that I want to use DDR. The VCK 190 also comes with low power DDR4, and so I could enable that as well, but we're not going to cover that in this example. When I did enable this interface, you can see here that all the DDR settings are now added to the NoC wizard. So here I have the basic settings for the clock frequency. I have preloaded the information for the various DIMMs that are on the part. Anyone who's worked on a board design before might know how you have to find the part and define all the timing parameters. It's very nice when you're working with an evaluation board where it will pre-populate these values for you. Next, I can specify how address mapping is done in the DDR and a few additional advanced settings. Now for this NoC, we're going to have this NoC only talk to the DDR, which means we are not going to have any master interfaces. So this is not going to control anything in any of our logic anywhere on this particular NoC. And we want to have 2 slave interfaces. We want to have the processing system be able to talk to the DDR as well as our programmable logic. So then I'm going to select 2 slave interfaces. Then the last thing I'm going to do is specify 2 clocks. You need to specify the number of clocks for the number of clock domains being used. The first one is going to be the processing system clock domain. The second one is going to be our programmable logic clock domain. So under inputs here, I'll have to select what I'm planning to connect these inputs to. And I'm specifically going through all of these settings here because these are the places where I find people run into trouble sometimes. So I know that this first AXI port, I want to connect to a cache coherent interface on the processing system. It's also going to use the ACLOCK 0 input. Next, it's already selected for me to have this connect to the PL, so I'll keep that the same. But I do want to change the clock that it'll be connected to, and that will be ACLOCK 1. If I go to the outputs, I see that there's nothing here because I have selected that I want 0 of them. And then under connectivity, I need to specify who's allowed to talk to what. And in this case, by selecting these 2 checkboxes, I am telling the NoC that the cache coherent processing system interface can talk to the memory controller, as well as the programmable logic can talk to the memory controller as well. I did notice that there was a question about quality of service, so I'll just quickly address that here, that there are different QoS type settings that can be made on this tab. For now, I'm going to leave them at defaults. All right, so now I have my NoC and it's enabled the memory controller. And I'm going to connect the first cache coherent interface to S0 AXI. And then I'm also going to connect the performance traffic generator to AXI 1. And then I'm going to take the clock, put that on A clock 0, and the PL clock on A clock 1. Now I'm going to also run connection automation, but just on the DDR NoC. And the reason why I'm doing this is because I want it to create the physical connections to the DDR4 interface as well as its reference clock. So by selecting OK here, that'll just load in that clock and the DDR interface. Now the next thing we want to configure is our PL only NoC. And so for this one, we want to be able to have the SIPs talk to an AXI BRAM. So we're going to have one slave interface, one master interface, and we're going to once again have two clocks. If I go to inputs, I'm going to be connecting to the low power domain processing system. That was that RPU NoC interface that I had selected in the SIPs. That's going to be on A clock 0. And then on the outputs, that's going to the PL. But in this case, it'll be on A clock 1. And then for connectivity, it has already selected that we want it to connect through. So then I can go to the low power domain AXI NoC interface. I can also connect its clock and notice how there's only one green check mark here. And that's because we told it that A clock 1 is going to be the programmable logic clock. And it knows that it's expecting the low power domain clock to be the clock that it sees here. So that's part of the validation. And that's also one of those things that I find people run into sometimes, like, oh, why can't I connect it? And more often than not, it's because it's expecting something different. And then I also want to connect this clock to the PL clock. And finally, I want to connect the master interface to the BRAM controller. So I have my two NoCs. I have the BRAM controller. I have the embedded memory generator. Now there's just a few other little cleanup things I want to connect. The block diagram will give a warning if I don't connect this traffic generator start bit, so I'm going to connect that. I also want to create synchronous resets to my PL clock, so I'm going to connect that to the reference clock. I'm going to take the reset and make that as an external reset in, and then I'm going to connect these to my peripheral reset ports here. And then finally, I just have two clock pins that I need to connect. All right. So this is our complete design. One thing that made some things jump around a little bit is that I had selected the reduced jog view because I wanted to make this more clean for your presentation purposes. But this is our NoC design. And sure, I practiced this before we were here, but it really would only take someone who's done this before roughly 20 minutes or so or less to get to this point here. So when I validate this design, it's going to say, hey, you've connected all these things to these AXI interfaces. They don't have addresses assigned. Should we auto assign them? In our case for this, sure, why not? And so now we can see that we have a NoC interface here where we're using the low power domain NoC interconnect, and that's what's traveling through this interconnect here, going all the way to this NoC slave unit, because in this case the SIPs is talking to the block RAM, AXI block RAM controller. And then here we have the NoC master unit, which is talking to the AXI traffic generator, as well as this master unit that is going to the DDR controller. Finally, I could just show under the address editor here, we have a few additional networks that we aren't connecting in this example, but you can see here that the traffic generator is connecting to base address 0 of the DDR, as well as the SIPs is talking to address 0. And then the BRAM controller has automatically assigned an address here specifically for communicating with that block RAM. And so when you would bring this over into Vitis to do the software or bare metal applications, you'd be able to do that. So that is the demo I wanted to show you all today. Hopefully it has, will help you save a little bit more time, and you've learned a few things that you may not have thought of before. Before we move over to Q&A, there are a few courses that we offer specifically on the Versal parts, the architecture methodology course, as well as a course specifically just on the NoC. That's a one-day course just for the NoC. And if anyone's interested in that, feel free to reach out to us through our website, bltinc.com. And I'm more than happy to take any questions.
Ellie, we have a couple of questions coming in. The first one is, how would you add the AI engines to talk to DDR?
Oh, that's a great question. So the AI engines, right, as part of the adaptable, as part of the intelligent engines of the Versal architecture, that would connect to the DDR by instantiating an AI engine core inside of the DDR, inside of the NoC. And so by selecting that the part that it's connecting to is an AIE, an AI engine, is how you would enable the AI engines to talk over the NoC.
All right, our next question is, would a designer ever not connect DDR to the SIPs block?
So, I've seen that type of thing before. If you didn't connect DDR, for example, to the SIPs block, then you wouldn't have a way to run software running on the A72s or the R5 processors. You could, however, create other memories in the adaptable engines, such as using the UltraRAMs to be a space for your memory to operate. So in those cases, you wouldn't have to connect the processing system to the DDR, and instead you could just connect the programmable logic DDR for your own applications if you'd like. But if you were considering that, you'd really want to give a lot of thought at the system level considerations of what might occur if you were to do that.
All right, our next question is PL always NoC master?
So anything can be a NoC master or a NoC slave. A NoC master is purely something that wants to initiate a transaction. So within the AXI spec, you would say, okay, I'm a device that wants to talk to DDR. The DDR device is always a slave device because it can't initiate a transaction. So as the second demo showed, I can have some PL devices that are NoC masters and some that are NoC slaves.
Okay, we also have a question. How does NoC and DDR MCs handle refresh cycles on the DDR? And then a follow-up to that, to be more specific, what is happening to the data stream during a DDR refresh? Is the data diverted temporarily to a FIFO in this case? Okay,
so you can think of the DDR memory controller if you've ever on another FPGA design worked with the memory interface generator. So that has all the built-in logic to be able to support a refresh. That I'm not sure of the specifics internally that handle that, but it would involve some amount of queuing and FIFOs and so forth to be able to allow for those refresh capabilities. And some of those refresh settings could be modified in the NoC configuration wizard. I hope that helps.
All right, next up. Is there a limit to how many NoCs can access a single DDR memory?
So the limit, it's not that there's necessarily a physical limit. It will create a solution that can access the DDR memories. What What you can run into is bandwidth limitations. So at some point, you're going to be, you may be trying to access the DDR so much that you won't be able to get full bandwidth, and you might starve some of your peripherals trying to access it. But other than that, there are those 4 memory controllers there, and really, to answer your question, it really would be on a case-by-case basis. There are, I believe, 6 or so separate inputs to each memory controller, and you'd have to come up with your own arbitration scheme such that it can handle all the bandwidth that you need.
Okay. Can NoC handle the situation when the slave lies in a different clock domain than the master?
Yeah, so that's a good question. The NoC handles the clock domain crossings at each of those boundaries. So like I showed in the demo, at any time you have something connecting to either the master or the slave, you need to specify which clock that is, and you give it that clock domain. And if, for example, you were to inadvertently connect the wrong clock domain, when you run the validation, it's going to tell you that something's not connected correctly, or it may even block you from connecting it at all.
Ellie, do the NoC switches support QoS and deadlock avoidance?
I think I answered this question a little bit earlier. There is that QoS tab, and there's a QoS report that is generated, and so you could use that and fine tune things as needed to get the best results that you're looking for.
Are there advantages to having separate DDR4 and for PS and a separate DDR for PL?
That's a very fair question. I've traditionally been used to, especially when doing Zinc MPSoC designs, separating that, especially if I have a design that's very high bandwidth on the programmable logic side. The processing system usage of the DDR is usually very low bandwidth, small amounts of transactions compared to things like the AI engines and the programmable logic. Really, the only thing you'd want to be careful of is your addressing. So if you have programmable logic that's using the DDR, you want to put that at a separate address range from where the processing system is, so that you don't have any address conflicts. But other than that, having a single DDR4 could be sufficient for most applications.
Okay, what is RPU?
So an RPU is a real-time processing unit. And this is one of the cores, one of the 2 types of processors available in the scalar engines of a Versal device.
Okay, that's all the questions in the chat panel. Does anyone else have any questions for Ellie? All right, thanks Ellie for demonstrating interfacing DDR with programmable logic for us. Folks, if you have questions, please go ahead. This last chance to put them in the chat panel if you haven't already. All right. I wanted to let you know that if you found this webinar interesting, you might also be interested in our Versal classes, particularly designing with the Versal ACAP architecture and methodology, and designing with the Versal ACAP network on chip. Both of these classes are coming up in June, and I'll drop those links in the chat panel to the course descriptions now. Also, sign up for our newsletter to stay up to date on all of our learning opportunities, including future webinars, and I'll drop that link in the chat panel too. Just checking any other questions from anyone? All right, I'm putting those in the chat panel for everyone. All right, thanks so much for joining us today. If you like this webinar and want to join additional webinars, please use these links to sign up on our website to hear about additional webinar series and training opportunities. It's bltinc.com. Thank you everyone for joining us today. Thanks, Ellie.
Have a good weekend, everyone.